In 1939, German mathematician Edward A. Heinrich Keller formulated the Jacobian Conjecture, which states that if a function from an n-dimensional space to itself has a non-zero constant Jacobian determinant, then that function must have a polynomial inverse. So to disprove this legendary conjecture would just require a single counterexample, some function that fits the conditions but does not have a polynomial inverse. Despite that, the conjecture evaded both proof and disproof for nearly 100 years. Again, it was formulated in 1939. However, it was pretty legendary, and it was the subject of many false proofs and claimed proofs from cranks and serious mathematicians alike. But recently, there was huge news. On July 19th at 10:19 p.m., Levent Alpoge announced on X that with the help of Claude Fable 5 and AI, he had found a counterexample to the legendary Jacobian Conjecture. Oh, God. He posted his counterexample on X, and it racked up over 30 million views. I guess a lot more people knew about the Jacobian Conjecture and were awaiting its disproof eagerly than I would have thought. And with the tweet, Levent attached a couple of computer verifications that this was in fact a correct counterexample. And I just thought that was a little strange, because you don't need a computer to check that it's a counterexample. And in fact, a lot of people were sharing or discussing this story saying that it was hand checkable. And yeah, it's hand checkable. Now, am I just here to flex that I had the endurance to do this? Yes, basically that is why I'm here. Since the counterexample was shared, there's been a lot of other interesting articles and writings and discussions about the Jacobian Conjecture and this counterexample. Terence Tao posted an interesting write-up about it, for example, but I'm not smart enough to give you anything like that, but I am stubborn, so let me walk you through my adventure hand-checking the brand new counterexample to this legendary conjecture.
Now, as we can see from the tweet, which will go down in mathematical infamy, we've got 3 points, this, and this, that are all mapped to this 1 point, -1/4, Before we get to computations, let's go ahead and write out the function counterexample in nice big math notation. Now, let's also write out the 3 points where the problem allegedly occurs. Already made a mistake in my writing because I forgot to write C3 equals here. Bear with me. Now, to show that this map and these points do in fact present a counterexample to the Jacobian conjecture, we are first going to evaluate the map at these points. Then, step 2, we are going to find the Jacobian. Once we've found the Jacobian matrix, we can take the determinant to find the Jacobian determinant and demonstrate that it is equal to a non-zero constant. It would make some sense to do step 1 last, just because it's steps 2 and 3 that would actually justify the Jacobian conjecture is supposed to apply in this case, and then doing step 1 would show that the conjecture is violated. However, steps 2 and 3 are the most work, so I'd rather do the shorter step first to gain momentum. But yeah, let's begin with step 1. And
now, the first step here, thankfully, was very easy. I figured first, let's just plug in the points, because Levent shared points with his X post, of course, and if you plug in these points to the function, they're distinct points, so they're supposed to go to different places. However, it turns out they go to the same place, and that's why we know the function doesn't have an inverse. If you've got these 2 inputs that go to the same output, well then, if you were trying to invert it, you wouldn't know where to send this thing back
points
to.
And verified the claim in the tweet. They all map to -1/4, Step 1 is done.
So the fact that the function's not invertible, that's the whole deal with being a counterexample to the Jacobian conjecture. However, the conjecture doesn't even apply to the function unless we check that important condition that it has a non-zero constant Jacobian determinant. So I did that part last because I knew that part was going to be the least fun.
Now, step 2, we've got to find the Jacobian. That's going to be a 3x3 matrix. In the first row, for example, it was going to be the partial derivatives of this first component with respect to x, then respect to y, then respect to z. And then the next row is going to be the same thing, but with this component, and then the last row with this component. It's been a long time since I did a bunch of partial derivatives. Let's see how this goes. We can also take a look at the time before I begin embarking on this journey, if you're curious. That is 8:36 p.m. I am not foolish enough to even consider trying to put all of these in a matrix, like on paper, the way it should really look. So the first row of our Jacobian would be this, and then this, and then this. All right, these could do with some simplification, but I'll leave it here for now. This is the second row of the Jacobian. All right, that one was pretty fun. All right, well, with that, we've got row 3. We've got row 2. It's this in column 1, column 2, column 3. And we've got row 1, column 1, column 2, and column 3. So I am somewhat tepidly going to put a check. All these papers come from my floor, so hair and dirt and grime gets on them. Done. Now, for the determinant, let me just show you roughly, visually, what we have to compute. The first part of the Jacobian determinant is to take this and multiply it by the determinant of this. The determinant of this 2x2 matrix is just the difference of the products of the diagonals. So really, we should start right here. The product of the partial of q with respect to y times the partial of r with respect to z, and then we'll subtract this. And this is probably as good a time as any to start using a different variable just to crunch down all these 1 plus xy's. Let's go ahead and just call them, I don't know, big A. Okay, this is the first term of the determinant. Now, the next part of the determinant will need to be subtracted, so hopefully we're going to get tons of great cancellation. The partial of p with respect to y multiplied by the determinant of this 2x2 matrix. So we have this. Keep in mind, this needs to be subtracted, so there's a negative that's not been accounted for anywhere in writing yet. The last part of the determinant will be to add the partial of p with respect to z multiplied by the determinant of this minor. Well, there we go. All that remains is for us to do this minus this, and then add this. So right now, if you couldn't tell, this is quite a lot.
Once I had put together the pieces for the Jacobian determinant, I had made a couple substitutions. A equals 1 plus xy and b equals 4 plus 3xy, just to try to condense the expression down. And then I went to rewrite it all on a separate piece of paper, and I guess it was wildly optimistic. I was just really hoping that some huge chunks of the expression were going to cancel out before I had to do any expanding. Obviously, I really didn't want to expand it term by term. I was hoping some big chunks would cancel out. I was not finding anything. So it dawned on me that I was going to have to expand it. But of course, it was really important that before going through the immense amount of work of expanding everything term by term, like, surely we got to be sure there are no mistakes up to that point. So I spent a lot of time, like, double, triple checking everything. I was already tired, but this had to be done. So I double, triple check, make sure everything's right up to that point. And thankfully I did that, because I did find a mistake or two, which I'll show you. But we had to make sure everything's good before we do the expanding, for sure.
I think some huge chunks might cancel out without expanding, but I don't think that's in the cards. And it's a good thing I checked a bajillion times, because not everything was correct. And let me see if I can find where the problem was. Oh, it's right here in the very first determinant row calculation. The biggest mistake, and really I should be quite pleased that this is the only huge, like, arithmetic mistake, is that I didn't combine these two factors of 3. So 3 and 3 right there, that should be 9, of course. Of course, since this is a negative, it should in fact be -9, and so I think there's also some potential trouble I got in with taking the x cubed out of both of these terms.
I also factored an x cubed out of the first part of the determinant, I think it was, and I did that in the stupidest way possible. Just totally playing with fire. I don't think I ended up making any mistakes with that. However, I did constantly double check and think twice about it. So that was totally stupid. I shouldn't have done that.
Yeah, so I guess what I'll do then is go page by page, determinant part 1, expand this, determinant part 2, expand that, determinant part 3, expand that. Those will probably all take up a page on their own, and then I'll just have to look, and hopefully we'll see a bunch of cancellation, and we'll be done.
And then we'll see a bunch of cancellation, and we'll be done.
Wow, that looks like that looks like fun. I've got one more term to include for 3yz times this bracket, but it's just not gonna fit here. I'm gonna have to put that one additional term down here. What a pain in the ass. So I just realized I've made a big mistake.
This is one of the most costly mistakes, if not the most costly mistake of this entire exercise, is that, I don't know, perhaps I was too close to the work. This is part of what I like about whiteboards and chalkboards, is you're able to step back from your math and take it all in, and like it really helps to get some physical distance when you're working with complicated expressions. But I was super close with all my lighting equipment blasting in my face and my microphone in my face, and I'm tired. And so it didn't even dawn on me that there were some like terms I could combine together before doing all of the expanding. And unfortunately, I didn't learn my lesson, because I will make this mistake several more times throughout the rest of this work, and I don't even want to know how much time neglecting that cost me.
All right, there we go. Isn't that awesome? Or maybe we'll do it differently. I don't know. Let's just move on to part 2. And we're in pretty high stakes territory at this point. With all the stuff going on here, if I make one mistake, it might just never get found.
When I said that, I did not realize how stubborn I was, and that I was willing to stay up all night looking for mistakes, because I was willing to stay up all night looking for mistakes, and I did.
Okay, the task at hand is to multiply this by this here in square brackets. That looks fun, doesn't it? I'm feeling good for the first time in a while. I'm going to put this on its own sheet, and we'll do this multiplication. All right, there we go. That is the expanded form of the second part of our determinant. This is the part that needs to be subtracted. I've alternated colors, by the way, just to make it easier to check my work if I do have to go back and check my work.
So I would say most of my process here is pretty good. I wouldn't make many changes. One of the best things I did was that alternating color strategy when you're expanding a bunch of terms. You don't want to do anything too obnoxious to indicate when you're moving from one term to the next. But alternating colors, that was perfect. Made it way easier to check my work, and it definitely reduces the monotony of staring at that paper when you've at least got two colors to look at. Goated strategy.
All right, had to take a quick intermission because my phone's battery died, but I'm back. Gum to obnoxiously chew, and I can continue doing my favorite thing, which is ungodly amounts of algebra. We are at 1:38 a.m. So I think we're nearing the end here. Let's keep on trucking. Well, this looks horrible. In case you were curious about my opinion on this, terrible. All right, now here's a funny thought. Oh yeah, that's gonna get hit by a 1. That might be our -2 right there, guys. Everything else, it's all gonna work out. You gotta trust in the process. All right, I guess all that's left now is to multiply this. I am not feeling very good about this, in case you were wondering, and then we can start, hopefully, cranking out the world's greatest simplification ever seen. This is what we got to do. We got to take this, part 1 of the determinant, subtract part 2, which is right here, and then add back in part 3.
I think at this point I was feeling pretty excited because we were about to start combining the terms for the final evaluation, where everything's supposed to cancel out and leave behind -2 as the non-zero constant Jacobian determinant value that shows the function is supposed to fit the conditions of the conjecture, or that it does, and so you would think it's invertible, but it turns out it's not. So I was excited to do that. However, I decided it would make more sense to combine like terms first in that first part of the determinant to hopefully lessen the load of work and then go from there.
They're just like, there's just a bunch of negative terms that are adding up. This is the x to the 6, y to the 4, z to the 1 term, -285. Awesome. Wow, this is just horrible. So many like terms and nothing canceled. This is, however, I mean, it's supposed to be the final stretch.
So then I finally got to start doing the check. I was really hopeful that it might just work, you know? So it's first part minus the second part and then plus the third part for this determinant evaluation. And I was pretty excited after looking at the first term.
X6, X7? X cubed YZs. They're going bye-bye. Hey, I don't have a lot of time. I gotta get back to finishing this. They say that's big air quotes. Checkable by hand. I decided, though, that for a video, I'm actually gonna check it by hand. All right, I love you. Okay, a little bit of delay there. My girlfriend just called me. I know, imagine that, right?
But my hopes were dashed away as soon as we got to the second term.
Ruh-roh. I'm gonna have to look through all this. Give me a second.
I actually got the best outcome here. Once I took a moment to slowly review everything, the terms here actually did cancel out. But then I moved on to the third term and once again encountered problems.
All right, we're at -72 plus 72. 1854, that's 72. It's 0 again. X to the 6, y squared z. Fuck. It's fishy to me that there was not a single other term of this form.
So I did some careful checking. I saw a term that was a little bit fishy to me, and once I double checked it, it turned out there was a factor of z that was supposed to be a z squared. So I fixed that, and things still did not work out.
Oh god. And I think that's it.
Then I found another z causing problems, a z cubed that should have been a z squared. So I fixed that, and then it worked. For that one term, it worked.
It should be z squared. And oh my god, look at this. Plus 54 x to the 6 y squared z squared plus 54 x to the 6 y squared z squared. That's 108. It zeroes out. Yes! All right, next term is, there's no way that this is gonna work.
And indeed, it did not work.
17. So -37. Damn it.
So at that point, I took all of my papers out to my living room where I'd have a bit more space to just be face-to-face with the algebra, get away from my studio with all the bright lights, and just look at everything really carefully. This might have been the most extensive proofreading I had to do. I can't remember. I spent a lot of time just staring at this stuff.
A coffee out, but mathematician.com, it's got Leonard Euler going through Königsberg and Seven Bridges problem. Really cool.
Trying to find a mistake and you know, hoping at every moment that I would find the error. And sure enough, I found some mistakes. One was just a basic arithmetic mistake. The other one was more significant. It was a 1 plus xy that was supposed to be squared, but I had forgotten to square it, so huge mistake. So I went ahead and fixed that, as well as the arithmetic mistake. But while doing that, unfortunately, I made an even more boneheaded mistake. I think when I was doing this, I was just so fixated on correcting how the one type of term that had caused the problem, correcting how that worked out. Those were x to the 4 y squared z terms. And I was so fixated on that one term and making sure that all the coefficients canceled out that I totally neglected the other consequences of my arithmetic error. My arithmetic error had multiple terms that it was impacting. And when I corrected it, I only updated one term. So I go through a ton of writing to make these corrections, but ultimately we know it's still not gonna work out.
And all we'll have to do is this part. That's all we'll have to do. All we'll have to do. All right, let's get to it. All right, check it out. And now I got it perfect, I'm sure, this time.
So now I combine like terms in the first part of my corrected Jacobian determinant.
All right, out with the old determinant part 1, expanded part 2, and in with the new determinant part 1, expanded part 2.
And then I check up through the x to the 6 y squared z squared term and find that doesn't work.
Yeah, negative 18 and then plus 54, x to the 6 y squared z squared.
But I was just stupid. I double checked and it did work. I just done the arithmetic wrong, so it did work.
I just made a mistake before because the third term, it works. That's it, right? That's it. Yes!
But then the next term, still, that didn't work.
Okay, so that did not fix it.
At this point, I was utterly exhausted, as you can imagine, but the sunk cost fallacy does have its upsides. So, I mean, you know, I was already this far in, like, I don't know, 5, 6, 7 hours. I was just gonna go through and finish it. The way I'd organized my work definitely made everything feel a little bit more approachable. And I can't help but think how easy this all would have been if I just not made a mistake. Like, imagine that. Imagine if I just not screwed up. If I had done this on a big fat whiteboard, not trying to record it, you know, so I didn't have lights in my face and a microphone in my face, then perhaps I wouldn't have made a mistake, or maybe I at least wouldn't have made as many. But, you know, I was this far in, I was gonna finish it. So I finally found that boneheaded oversight which I had made earlier.
All right, after painstakingly checking everything again, I realized I made a very embarrassing error.
The fact that an 80 was updated to a 90, but that was supposed to impact multiple terms.
However, that has more implications than just changing this number, because the 80 should have been a 90 over here, which means the distribution of these parentheses across this bracket, you know, there's a bunch of other terms that hit this.
I fixed that and rewrote whatever that was, the third part of the determinant, and then I started combining the terms.
I guess I'm just gonna rewrite this whole thing, and then then we'll try again. All right, like terms combined, there is the third part of the determinant. Definitely looks a lot nicer this time around. And here are our other two determinant pieces. All right, it's time to attempt the final determinant calculation once more. I've really got a great feeling this time. It's all gonna cancel out.
And then the craziest thing happened.
X cubed, that's it. Okay, first term still works. Yeah, we're good. Okay, second term still works.
It worked.
On to the third term. We are approaching new ground, but not quite. Negative 54 x to the 6. That brings us to negative 90. And as if by magic, right here, plus 108 x to the 6. Y squared z squared, 30 x to the 4 y squared z. Subtract this, then negative 216, oh my god, plus 216 x to the 4 y squared z, minus 108 x to the 5 y cubed z. There's an, then minus 3, and minus 72, 432. I didn't think we were going to see this 5 y cubed z. Would you believe it? 2 of determinant part 1, expanded part 2 corrected. X to the 7 minus 72, unless I'm missing something. Right there, plus 72 x to the 7 y cubed z squared. Woo, baby. I am allowing myself to believe. And would you look at that? It's only 5:04 in the morning. Okay, minus 204 minus 330. Right there. Minus 18 plus 18 last term. X to the 8, y to the 4, z to the 2. Minus 90, x to the 7, 90, x to the 7, y to the 5. 56, x cubed, y cubed. Minus, that'll be minus 142 cubed, x cubed, y cubed, plus 140. Okay, we are at 6, x to the 4. That'll bring us to plus 444, x to the 4, y to the 4. This is unbelievable. Minus 162 to minus 300. Okay, 378. Pull through for me here. X to the 5, y to the 5. Minus 108. Please God, on the third page. 108, x to the 6, y to the 6. 18, x to the 4, z to the 2. 18 x to the 4 z to the negative 18 squared z. It's the very first term, 48xy minus 48xy. What is there one thing left over here? So the final term.
Now, miracle of miracles, it came down to the final term, which was a 48x squared y squared minus 126x squared y squared. So it's a minus 78x squared y squared, but that's in the second determinant, so that's getting subtracted. So that's plus 78x squared y squared, which means we're looking for a minus 78x squared y squared to cancel that out in the third part of the Jacobian determinant.
78x squared y squared. Where is it? No, yeah, minus. Minus, we're looking for minus. Minus 78x squared y squared. Oh my god. There is one thing left here, folks. One thing which has not been canceled out through all this algebra. Do you see it? Oh yeah, you do. I know you do. It's a non-zero constant. A non-zero constant known as -2.
So yeah, I would say I am thoroughly convinced at this point that Edward Heinrich Keller's Jacobian conjecture is false.